very first, I would like to thank you for coming out this evening. I hope I managed to entertain you. Secondly, I would like to thank Professor Ajit of IUCAA, who has managed to arrange this for me. And he doesn't know this, but I would like to share with you that this is a special thrill for me to be here. Not the least because this auditorium, this building, is named after Chandrasekhar. The lecture series is named after Chandrasekhar. I am Chandrasekhar's academic grandson. So there is a link back here, and so it's special to be here. I also would like to thank Infosys and the Indian Institute of Science for awarding me the Infosys Visiting Chair Professorship, because it's given me a chance to spend an extended amount of time in India. It's coming up to, over the past 2 years, I've spent close to about 5-6 months, and there'll be a few more months that I'll be coming back again. Not only do I have had an opportunity to meet a huge number of very brilliant students, but I've had an opportunity to now start to work with a lot of people, as Sudhanshu mentioned. And I've also had the opportunity to visit my ancestral village in Kutch, so where I discovered that 25% of the village was related to me. So you can imagine this is like that Indian movie, right? You show up in a village and suddenly half the village or a quarter of the village wants to invite you to their home to sit and meet and greet, and so it's been a huge thrill for me to be here in India over the past few months. Today's lecture is titled, How Did the Universe Come to Look the Way It Does? It's a bit of a cumbersome title, but I couldn't come up with anything more creative or fun to put there. As I start, the first few words that I should be saying are the standard words that every astronomer says when they give a public talk. Since the dawn of mankind, we've been fascinated by trying to understand the universe around us. But I think the real point to start the story is about 50, 60 years ago, maybe a little earlier, where we started to make huge leaps in trying to make sense of the universe. Astronomy and astrophysics and cosmology started to become observationally driven, data driven. We started to have telescopes up in the sky, both on the ground and up in the sky, that began to give us data, concrete quantitative data about what the universe looks like in its infancy, what the universe looks like today, and what it looks like at various epochs along the way. That's a huge achievement in its own right, but that's not science by itself. Science also involves trying to make sense of how that progression happened. And so I will share with you both a little bit of a summary of what we have learned from observations, but I will also share with you in the second half of my talk, how do we go about trying to make sense of this? And so let me start. A good place to start is our Milky Way. So the Milky Way is a galaxy. It's our galaxy. It's a galaxy that resembles a pizza, basically, made out of stars. It's a flat, circular structure made up of stars. There are close to, as it says up there, 100 billion stars in our Milky Way galaxy. Nearly as many stars in the galaxy as there are neurons in your brain. Now, our sun happens to be one of the stars in the galaxy, and that star happens to lie about 2/3 of the way out from the center towards the edge of the galaxy. So this is just one of the many objects that we see in the sky. In fact, because we are living in the pizza, the band of the Milky Way that you see in the sky, especially if you're in a rural area here, I can imagine that most city is light polluted, just like it is in anywhere else in the world. But if you are in a rural area, you will notice that there is this band running in the sky. That's the band that you see of the pizza. Imagine you're standing inside the pizza and you're looking towards the center, you will see the dough. That's the dough. But there are stars around, and those stars are the dough that makes up the pizza around us, local dough. But I'm not going to talk about the stars. What I want to talk about is other galaxies. And you can see them in the sky. The sky is sprinkled with other galaxies that are too faint to be seen mostly with naked eyes, but you can see them with powerful telescopes. So these are examples of kind of galaxies that you could see. I see that there are a lot of astronomers or astronomy graduate students in the audience. Don't take this too literally. These are not the exact positions of these objects, but they are examples of the kinds of things you would see. Now, when you look up in the sky and you see this ensemble collection of galaxies, you will notice that there are galaxies that look like our own. They are pizza-shaped, they have a little bowl of stars in the center, but generally they have a flat pizza-like this shape. But then you also have galaxies that look like this. They are giant spherical collections of stars. And they are known as the elliptical galaxies, they're known as the elliptical galaxies. Let's just leave it at that. It's the simplest way to think about it. In fact, when you look at the entire sky and map out the zoo of galaxies, this is what it looks like. There is a huge variety, a huge diversity in the population of galaxies across a variety of shapes, a variety of sizes. And just to pick out a few, you have a handful of galaxies here that look like those bowls of stars that I showed you just a few minutes ago. There are galaxies that look like our own in the sense that they are flat, but they have very different features in them. Some of them have very beautiful extended spiral arms. Some of them have spiral arms that have many spiral arms, but they are wound around, and others have tight spiral arms that almost look like rings. And then there are galaxies that look like they have no distinct shape, if you will. They're amorphous galaxies, and they're called irregulars. We have a huge variety, as I say, and at the center of our galaxy sits a gargantuan black hole. This black hole, in terms of equivalent mass, is about 1 million suns, our sun. And if you've seen the movie Interstellar, I believe, that's an image of a black hole. And I'm going to share with you just a little bit of a story that goes with it. This is an authentic picture of what a black hole would look like. If it was accreting gas, you notice that the gas looks like it's coming around in a disk in the front and then sort of goes up and around the top of the black hole. That's not what's happening. What's happening is that the gas is just going around like this. But because light is being bent by the gravity of the black hole, the image looks like it's forming a halo on top of the black hole. Now, I told you that I would share with you a little bit of a story. So, for the longest time, we knew that this is what happens, but we had no way of actually building a model, a real, genuine simulation, because it took too much computational power. It would be very, very, very expensive to make a picture like this using real equations, real Einstein's equations. Kip Thorne, who's a general relativist who studies black holes, managed to convince Hollywood to fund it. So they get to use this picture in a movie. He gets an authentic science quality simulation result of a black hole. So he's written several papers on this simulation, in addition to getting billing for being the scientific advisor to the movie, and probably a lot of money to go with that as well. These black holes in many of the systems. So first of all, I should mention, there was a note in the last slide that nearly all galaxies have black holes in their centers. And these black holes often have gas swirling around them. And now when this gas swirls around a black hole trapped in its gravity, it is rubbing, friction, it's heating up. Just like when you rub your hands together, you heat up. Same way the gas is heating up. And as it heats up, it radiates. And so you have radiation that's being emitted by this one black hole can exceed the light of 100 billion stars. So it can outshine all the other stars in a galaxy. That's how bright it can get. In other galaxies, the gas is turned into a jet that literally pierces out into space, out to vast distances. These images here are actual images taken for a black hole in an elliptical galaxy, not too far away from us. There are images taken by the, I've forgotten what EHT stands for. Anybody? Event Horizon Telescope, right. And then there are various other radio telescope images. You see the jet right there. You see features that look like this, which means the jet is basically spinning, which means the black hole is spinning. And it's spewing its fiery breath, if you will, all over the place. And if you move out and look at this from zoom out and look at it from a large scale, you can see features like this. Now, just to give you a scale, this is the central galaxy. This is the jet in the central galaxy. These are large bubbles that represent explosions from this black hole that occurred many, many billions of years ago. But see how large they are. These black holes can literally transform their environment around them. So, tiny little object, as compact as our solar system, literally, can impact a region that far exceeds the size of the galaxy. So we have a lot of complicated physics going on in the universe. So when I say the challenge is to make sense of all these observations, I really do mean it's a huge puzzle to start with. We have tons of processes that we need to understand, tons of observations ranging from X-ray to radio to optical to infrared. We have all these images that are showing us different parts of the universe, a different image of the universe, and our job at some point is to try and make sense of all that. Now, let's return back to the galaxy. This is an image from the 2-mass galaxy survey. Ignore this band right in the middle. That's our Milky Way. It's sort of ruining our image. But if you focus up here and you focus down here, you will notice that every dot there represents a galaxy. And what you will notice is that it looks the same up here as it does here. Okay, there are a couple of smudges here. Those are irregular galaxies that are in orbit around our own. So if you go in the southern hemisphere, you can actually see them in the sky. But we won't worry about that because they are related to our Milky Way galaxy. Whereas these galaxies are far beyond our own. And if you look at how they are distributed in the sky, you see that they look more or less homogeneous in the sense that it looks the same everywhere in the sky. But is it really? Now think about it. If I'm standing here and if I had no perspective sense and I took a picture of this room, then the front row and the back row would all look squished together. I wouldn't be able to tell who's in the front and who's in the back, and everybody would look smushed together to the extent that the empty rows here and the empty rows elsewhere would vanish, right? Everybody would look like it's just the same everywhere. However, if I could tell how far away you are, and I know that most of the front row is empty, then I can start to figure out, well, wait, these two guys are friends, they're sitting over there. right? I can start to piece together how galaxies are organized, who are groups of friends sitting together. Now, we can do similar things with the galaxies because we can map out how far away they are. And when we do that, we start to see that they are organized in these chains. If you look at these maps as they're flashing by, first thing you should notice is that there are these huge chains of galaxies. The second thing you should notice is that there are empty regions in these galaxies. So there are these large empty regions where there are no galaxies. So the sky is actually not homogeneous in that sense. You can superpose all those maps that I showed you, and you can see literally these chains as they exist in the sky. There's the Milky Way. But the other thing you should notice, in addition to these regions that are large and empty, you should also notice that there are regions where the filaments, these chains, cross. There, you have a huge concentration of galaxies. And in fact, in these regions, there could be up to 1,000 galaxies caught in their own gravity, whirling about. These regions, as I've written up there, have a mass that's equal to 1,000,000 billion times the sun. So they are amongst the most massive objects in our universe. They are full of gas that's radiating in X-ray. So now we have X-ray to make sense of, optical to make sense of, radiation that we're seeing in the entire spectrum that we have to make sense of, trying to understand how this universe looks the way it does. And this is just a little graphic that shows you that these galaxies are moving at about 1,000 kilometers per second, very, very fast, but they are not going anywhere because the tremendous amount of gravity keeps them bound together. So they spin out, they turn around, just like when I throw a ball up in the air, the ball goes up, comes back down again. The gravity of the Earth holds the ball. The gravity of this object is holding these galaxies together. Now, telescopes are really time machines. The further back we look, the further back in time we are seeing things. And so we are here. Relatively near us, close to the present day, are the galaxies that I've been showing you so far. But we can start to go back further and further. So Hubble Space Telescope can go all the way back to roughly 500 million years after the Big Bang. And you've all been hearing possibly about the Webb telescope, JWST. That telescope can go as far back as 200 million years after the Big Bang. And so we can start to get an idea of what the universe looks like back at 200 million years, when it was 200 million years old, when it was 300 million years old, 400, 500, and so on and so forth. So we have slices of images of the universe as it was at different times in its lifetime. This is like taking an album and looking at your pictures when you were 1-year-old, 2-year-old, 3-year-old, and so on and so forth. So we have the capacity to do that. In fact, we can go a little further back than that. But before I do that, let's talk about what James Webb Telescope is showing us. Well, one of the great achievements of the Webb Telescope is that it has revealed to us that shockingly, and this has come as a somewhat of a surprise, that the first galaxies, these objects, formed when the universe was only 300 billion years old. That's tremendously fast. That means things formed and started to form stars and became bright enough so that we can actually see it. And some of these objects are massive galaxies. They will become those giant galaxies that we see today. The furthest back we can look is roughly about 375,000 years. At that point, we're looking at the radiation that fills the entire universe. We're looking at the radiation that came from the Big Bang itself. And we can look at the patterns in this radiation. Now, to imagine the patterns in the radiation, how many people have looked at a swimming pool when there's light shining from the top? You've seen patterns of light, or you do this in a lake, or on a shore, or on a beach. You can see patterns of light moving. These patterns of light is because light from the sun is coming and it's bending and it's creating a pattern. In the same way, there are structures, there are ripples in the early universe, and these ripples are bending the light, the radiation, and we can see these ripples. These are tiny little ripples. You know, when you're standing by a lake and a wind is blowing and there's this tiny little waves starting to form? This is tinier than that. In fact, at one point we had tried to figure out an analogy for it, and it's like taking my hair and dropping it on a lake or a puddle and basically saying, can I tell that that's my hair floating? That's the relative size of these kinds of ripples that we are trying to observe. But we do it, and the very first time this was observed was in 1992. And then over the course of a few years, we had telescopes that go up in the sky that made successively better maps, more higher resolution maps, more detailed maps of this microwave background. Just to give you an idea, at least when I was a kid, if you turned on your old-fashioned TV with the antennas and there was no signal, you know that static that you got? That static is basically, part of it is the microwave background. You're seeing the microwave background on your TV screen. I didn't learn about this until I got to Princeton, and people like Jim Peebles, who were amongst the people who discovered the microwave background, predicted and discovered the microwave background. They were telling us this was like, you know, how you get nerdy graduate students hooked onto this kind of thing. It's one of those stories that you remember. But this is this noise pattern that exists in the Big Bang radiation. It shows right there that these ripples are tiny, 1 part in 100,000. But these ripples tell us what the fluctuations in the matter was back when the universe was 375,000 years old. And the idea is that these ripples, these tiny little waves, eventually grew into galaxies, into these filaments that I showed you, and literally span the structure that we observe in the universe. The question is how? And the question is, am I pulling your leg? Can I actually show you that that's the case? So before I start talking about that, let me just put this in a flowchart. We have the microwave background. We have tiny little ripples in the matter in the universe back at 375,000 years. Then by 300 million years, you already have the very first galaxies. You have galaxies in the present-day universe. And then you have clusters of galaxies. You have filaments. You have disk galaxies. And then these are the things that I'm going to now start to tell you about in the second half of this talk. So just to put this in context, this image is a good way to think about what I'm saying when I say, can we make sense of all this? So it's an image taken at the same point in the Arctic by a difference of about 100 years. 100 years ago, you looked at this patch of land and there was all this snow and ice and glaciers. Today, it's barren. Now, you could take a picture, it's a nice National Geographic type picture, and you can leave it at that. Or you can ask the question, what happened? How did this ice disappear? It could have disappeared all overnight. or it could have disappeared slowly over time, or it could have just stayed along perfectly the same for literally 70, 80 years, and then in 20 years it disappeared. Now, most of us know what's going on. This is climate change. The Earth is heating up and the glaciers are retreating. But how did we know this? Because scientists who study climate went out and started doing very detailed modeling to understand what was happening to the Earth. In the same way, when we try and make sense of all those images that I've been showing you, we need to start modeling. Now, I can't just take any random models. I have to start with the image of the universe at its infancy. I know what the ripples look like. That was a starting point. But what else do we know? We know that there's gravity in the universe. So that's the first thing that I can play with. I can't just put in any gravity. It's the gravity that we see around us. Gravity, gravitational law as we understand it today. So the question is, if I use gravitational law as I understand it today, can I understand what is happening and try and make sense of all those observations? That's the game. That's what the next phase of this talk is. That's what people like myself do. Now, as I say, we know that matter responds to gravity. We know gravity is present, and we know how gravity works. So how do we go about trying to make sense of this? Well, we can't repeat the Big Bang. But what we can do is we can set up a big box on a computer. We can put matter down on this box. We can put ripples in this matter, like on a computer. Then I can load this into my computer, code up gravitational law, so every piece is attracting every other piece, and let it run and see what happens. Now, just to make this first, to give you an image, if this room was exactly the same, and there was gravity pulling on each one of you, and you were sitting there in the middle, and everybody was equally spread out around you, what would happen? There is no force, no gravity really acting on you, because you'd be pulled in that direction as much as you're being pulled down. And you'd be pulled to the right as much as you're being pulled to the left. So without those ripples, nothing would happen. Those ripples are critical, because what they do is they turn the room into what's looking like here. So there's a 4-people group here, 3-people group here, so there's more gravity here. There's 4 people there. There's much more over there, so there's a lot more gravity over there. What's going to happen is that you guys are going to slowly drift over there, because gravity is going to pull you. Gravity is a capitalist system, I hate to say, because the rich really do get richer, and the poor get poorer. And so you guys will all drift over there, and that group over there will just get bigger and bigger and bigger. And you'll have an empty region forming in the center. So now think back to those pictures I was showing you. Filaments, clusters, and giant empty regions. Giant empty regions have been emptied because gravity has pulled out the matter into the filaments, and then along the filaments into the clusters. And that's how we see things starting to form in these simulations. So let me show you that. This is a box of one of those simulations. Right now, we're only doing simple things. It's just matter and gravity. Nothing more complicated than that, right? We'd like to start simple and then make it more and more complicated. So let's do the simple thing. Let's run the simulation forward and see what happens. Now, you see these patches of blue. It looks like smudges of blue. That's the ripples. And because they look like smudges, is because the ripples are really, really small. Now, let's see what happens. The rich get richer, and here the rich get pinker, and then they become yellow. And you can see strands of filaments starting to form, and you can see empty regions starting to form. In other words, matter is being drained out of these voids and driven into filaments, and then driven into clusters. So we can get an idea of what's going on here, but life's not that simple. Because the universe, before I get to that, I forgot. It looks like if I just took that simulation and I plunked down all the matter as if I was looking at it from the center out in some sense, and I mapped out what they look like, this is what they would look like. Now, blue or red, one of those is real observations, and the other one is from a simulation. And I would challenge you to try and figure out which is which just by looking at it. And the chances are you can. And in fact, if you do mathematical analysis, you do statistics, you find that it's more or less the same. Just for your record, the blue are the real observations, and the red here are the simulations. Okay? But the point is that we can actually start to make large structures in the universe that look like the real universe. And all I did was start with little ripples and added some gravity. But now let's move it a little forward. The universe, as I say, is a little bit more complicated than that. It's not just made up of matter, without getting into details of what kind of matter makes up the universe, let's just say that the universe is not just made up of matter that responds only to gravity. There is other kinds of matter, like the stuff that makes us up, the stuff that makes the earth up, the stuff that makes the sun and the stars. And this matter, which I will refer to as ordinary matter, heats up, cools down. It resists squeezing because it can heat up because of pressure. When it cools down, it's radiating, and so it glows. Now, you all know this intuitively. If you take a cup of chai, a hot cup of chai, and put it on the table and start talking, what happens to that cup of chai? Cools down. Why did it cool down? Because it radiated away all the heat that was in the cup. And so that's the process that we need to worry about. We need to worry about what's happening to this matter as it's being moved around in the universe. Because at the end of the day, what we observe through our telescopes is not the matter that only responds to gravity. We see the stuff that heats up, glows, and cools down. So the question is, can we put in this other kind of matter, this ordinary matter, into our simulations and try and form galaxies? So that becomes the next phase. But the problem here is that the number of things that I would have to worry about start to become incredibly large. And it becomes incredibly complicated. You know, when you rub your hands together fast, you feel heat. That's because there's friction. So I have to worry about friction. I can't slide on the stage because of friction. So then I would have to worry about friction. I have to worry about drag. I know you're not allowed to do this, but how many when you were a kid, you're driving along in a car, you stuck your hand out of the window, right? You feel this push, there's an air out there that's feeling like a wind and it's blowing your hand back. That's drag from the wind. We have to worry about the drag. And then there is a whole bunch of other things that we have to worry about. Gas, when it cools down, starts to form these dense nuggets, and dense nuggets will then start to form stars. So we have to worry about star formation. We have to worry about stars when they end their life. They explode, and they spew out everything that's in their center, plus it's like a huge explosion to begin with. So we have to worry about that. We have to worry about black holes that are glowing tremendously bright or are shooting these jets out into space, out to vast distances. We have to worry about explosions of stars. Yeah, I think I've covered at least the images that are up there, but there are a zillion other processes that you would need to worry about. So this is not for everybody. This is just for those people who are especially interested in all the details. This is just a list of some of the things you would have to worry about. So radiation from the stars, from the black hole, gas is heating up because of these explosions. You have gas cooling down. You have magnetic fields. You have all sorts of things that are happening. Gas cooling falls into galaxies, turns into stars. Then it starts to go through this whole process. You have drag going on. You have conduction going on. Conduction is basically when you have hot things sitting next to the cold thing will start to heat up. So we have to worry about that because it's energy that's going from one thing to the other thing. All of these things we have to start worrying about. In fact, the honest truth is that even the most powerful supercomputers in the world aren't good enough to be able to handle all the details. So we have to start making some choices. We incorporate some of them and ignore others. One of the things in the abstract was, what are the successes and challenges? And where are the opportunities? One of the challenges is that we cannot put everything we know that happens. And we have to make choices. And one of the questions is, are we making the right choices? The second thing about the choices is that some of the choices we make to put in, we have to fudge it. Because our simulations are not powerful enough to be able to resolve tiny little details. So we have to put it in some ways, and sometimes we have to make approximations. And the question is, are those approximations right? Now, before I go on, you are seeing this movie play out in the background. This is a movie that has been made by a group, a collaboration, written here, illustrious TNG collaboration. They have a huge amount of resources so they can make IMAX quality movies. So I've stolen their movie to show here. I'm sure they won't mind. Publicity is a good thing. But you're seeing these filaments forming. You see galaxies forming in the filaments. You see galaxies draining into these clusters. You see clusters. You see stars exploding and then large explosions blowing up into the interstellar, into the space around galaxies and out to vast distances. You see gas outside the galaxies starting to heat up. And so this is going on and on over time, over 3 billion years. This is a process that's happening. But at the end of the day, these blue galaxies, if you zoom in and you look at them, you find that they look like this. And you see they look like our galaxy. And they look like those other stars, galaxies that I showed you, the ones that look like balls of stars. In other words, we can now start to reproduce the universe in even better detail than I showed you earlier. Not just the filaments and the voids and the clusters, but inside the filaments and inside the voids, drifting along are galaxies. And these galaxies look reasonable. So now we're starting to make a better sense. And as I watch this movie, I can now make sense of what's happening over 13 billion years. I know what it started like, but now I can follow it as it's going along. I know where the wind was coming from, or what happened to this galaxy. And I can track the entire motion, the dynamics of the universe, step by step by step in this way. But as I say, you have to make choices. And sometimes we have this, I can't do friction. So I have to figure out some way to model friction in my simulation. My computers are not powerful enough to go from huge scales of the universe down to scales where friction is important. So I have to figure out some way to put it in. And different groups make different choices. Even though the physics is the same, we have to figure out how to be creative in putting them into the simulation, just because our simulations aren't powerful enough. But choices can have an impact. So I'm going to play this movie. This is 4 different simulations. This one, the label has disappeared in the beginning, but it will appear in a second. And what I want you to see and take a look is, as it's the same conditions, same patch of the universe, just being run with different simulations that have used different choices. What I would like you to pay attention to is what happens as the time goes by. So, at the start, it looks very much the same. It's behaving exactly the same. Then the first galaxies form and you start to get these explosions. Now look at this simulation called Simba. The hot gas is escaping the galaxies much sooner than it is in any of these other ones. Magneticum is coming up next. But Simba is actually predicting that the universe today has been heated up. These guys, not so much. So there is a difference between this, and this universe. Now you may say, oh my God, that means that you guys don't know anything. It's true, at some level. We don't. We're scientists, we're trying to figure things out. But this is a good thing. A good thing because I can now make tests. If this is saying that today's universe should be hot, I can go out and make observations. Or my colleagues can go out and make observations. They can test this model, and they can say, no, something's wrong here, your model's not good enough. You need to fix whatever assumptions you've put in. And so step by step, we cut away, we improve our models. And step by step, as we improve the models, we replicate the real physics that should be there. Even physics that we do not understand, and there's a lot that we do not understand, we start to make sense of it by this trial and error. So, you may have heard in the newspapers, astrophysicists completely baffled. JWST has found these galaxies at 300 million years and their models can't do it. We need to rethink astrophysics. Nonsense. This is somebody who's trying to sell you newspapers. Right? We can do our simulations. And if we do them properly, we can ask, do we see galaxies like that? And the answer is yes. Do we see as many galaxies as JWST is? And the answer is again, yes. And then what? Well, the great best part is I can take that galaxy in my simulation and I can follow it until today and ask what happened to it. And I can start to ask all sorts of interesting questions. So, as I say, the physics really is complex. But we have a big picture that is pretty good, works remarkably well, and more importantly, we have started to get a handle on the details. We're starting to put in the right kind of physics to get the right kind of galaxies forming, and we can make connections across all those images that I was showing you in the first half. In the past 25 years, with the advent of supercomputers growing in power, in leaps and bounds, we too have been able to make much more sense of the universe. And so, as this image shows, pieces of the cosmic puzzle are starting to fall into place. I will not claim that we have all the answers. I will not even claim that we have most of the, a large fraction of the answers. There's a lot that still needs to be done. But when you think about where we started, just in my own academic life, in '89 when I graduated, we could barely run things on a computer. There weren't even such things as supercomputers at that time. But now, with computers as powerful as they are, I can make movies like this. The ones I showed you. And so as you look at this movie, think of where we were think of where we've come. But the message I would like to leave you with is that we have made huge progress. We have the capacity and the ability to start making sense of the entire history of the universe. We can start from 300,000 years, and we can figure out how the universe evolved over some 13 billion years. For humankind, I think that's a huge, significant achievement. When you think about the Greeks, or you think about the Harappan civilization, in the case of the Harappan civilization, it's a little bit more difficult because we cannot translate their texts. But with the Greeks, we have been able to translate their texts. With the Babylonians, we've been able to translate their texts. And with the Egyptians, we can translate their texts. We don't think about the little details about what they did. We don't worry too much about what they did in terms of their everyday lives. What we talk about when we talk about achievements is the achievements in the history of ideas and the way they achieved in the sense of perceiving and comprehending the universe. This is our legacy. And so this is why science is so important. Of course, the legacy spins out. While I run supercomputers and challenge them where IBM gives me free time to do this, those computers get better and better, and then they're applied to everything else. So the kind of work I do and the kind of economic activity that gets generated out there is all intertwined. Knowledge is knowledge, and progress is driven by knowledge. This is our legacy. Thank you.
Hello, yeah, that's a really amazing talk, and I think that I am very sure that you have a lot of questions to ask. I would request Saurabh to at least to take one mic, and others please raise your hand if you have any questions, please.
So thank you very much. What is the expected life of this JWST?
Oh gosh. I'm a theorist. I don't know these answers, but my colleagues are in the audience. Anybody know the answer to this question?
The expected lifetime?
Yes.
So it's constrained by the amount of fuel that it has, but they saved some fuel when they got it to N2, so it's expected to last about 20 years.
There you go.
And then what is the next milestone? Because after Hubble we had this JWST.
Yeah, so NASA has just gone through various processes to narrow it down to 2 telescope missions. European Space Agency has been doing the same thing. I know that India is in the process of they have 2 satellites that are sitting on the table, and they're trying to decide between those. Israel is trying to make a decision. So there are a whole bunch. One of the Indian telescopes is actually, for me personally, very important, because there is this part of the radiation spectrum that we have sort of ignored. It's the ultraviolet radiation. Between the violet and the X-rays, there's this band where if you want to look at stars being born today around us, young stars, that's the band you really want to be in. And we don't have any telescopes in that since Hubble was recalibrated, or instruments on Hubble were changed early on. So, that's a very exciting mission. I personally would hope that gets pushed forward and launched. So there are missions in the pipeline. X-ray missions are in the pipeline, for example, in the United States. Yeah.
Thank you.
In July, we had the first data release of Euclids, and when I was classifying those images, I noticed that there were much more elliptical galaxies than spiral galaxies. Why is it like that?
In sort of what area?
I was classifying the images on the Zooniverse platform.
These are Euclid citizen science.
Oh, Euclid citizen science. Are they targeting clusters then?
I don't know.
So there are parts of the region. You know what I showed you about the clusters of galaxies? One of the things that Euclid is trying to do, at least in its early stages, is to look at these large concentrations of mass and look at the distortions due to gravity that's being caused by them. But these regions, these cluster regions, are heavily populated by elliptical galaxies. So it's possible that you were looking at one of these regions.
I remember they're looking for strong lenses.
Yeah, okay.
Galaxy lenses.
Right, so that could very well be, because elliptical galaxies are also amongst the most massive galaxies. So if you were right now trying to find places where you had strong lensing, where light is being bent, where gravity is strong, you want to pick out the biggest galaxies. And so again, that would give you this bias. But really, if you looked at the universe as a whole and look at the populations, the disk galaxies are actually more in larger numbers.
So maybe I would like to ask you, based on your simulation, whatever you have been showing there. So the amount of ripple effect or the distortion been added at the initial stage of the formation of the universe, will it limit or will it slow down the expansion of the universe where we are right now, or which model is
Okay, yes.
matching the current state?
So
what will be the future?
Yeah, so that's actually a very good question. So up to this point in time, at the present, the model that we've been using is a model that is being dominated by this a form of energy called dark energy, which we don't truly understand, but has the property that it's actually causing the universe to expand faster and faster and faster. That's the model that the simulations are using. Now, interestingly enough, there are two experiments. So one was mentioned, Euclid, and the other is the dark energy survey that's going on in the States. And they are trying to pin down the exact nature of some of these processes. So, for example, if it turns out that dark energy itself is changing with time, so that it's sort of getting lower and lower and lower, then the universe will not expand forever. But if it's not changing, then the universe will expand faster and faster and faster. So if you're asking me about the future, I think that's a really interesting question, and I hope that in the next 2 or 3 or 5 years, we will actually have an answer. But stay tuned. That's the best I can say.
Good evening, sir. Thank you for the talk. So we know galaxies formed because of the ripples that were there in the beginning of the universe. Why did the ripples form? Like, why wasn't mass evenly distributed throughout space?
You mean why were there ripples there?
Yeah.
Oh, that's an interesting question. Yeah, no, that's a difficult question to answer. So let me try and. Okay, so if I took a little cube here right now of air, and I asked you how much air molecules are in here, the answer is it's not the same as over here, because air molecules are continuously moving. So molecules are moving in and moving out. So at any given point in time, there'll be more particles here than over here. A really good example is if you look at soda water, right? If you fill up a glass with soda water and you watch it, what happens? Bubbles start to form. Why are bubbles forming? Because carbon dioxide is moving around and forming little pockets. and then the pockets grow a little bit and they start to rise. So basically, things are always in motion. In the early universe, the universe itself was tiny, and it was being, its behavior was being driven very similarly that we see atoms being driven. And so, if you're familiar with quantum mechanics, then that's what it was. It was quantum mechanical at that point. Things were changing, and so the ripples were forming and disappearing, but the universe was expanding at the same time. So as the universe expanded, those ripples got frozen. At some point, it became so big that there was the ripples on the small scales were changing, but the big scales were freezing in. And so the ripples that were happening when the universe was tiny got frozen in. Now, the universe was actually expanding very, very fast at that time. And so you could freeze it in. So in some ways, it's very similar to if you were to take soda water and put it into liquid nitrogen and just flash freeze it. You would get, water would freeze and then you would get these bubbles frozen in. And then you can ask the question, why is this glass not uniform? Why are these pockets of air and here is water? In a similar way, I'm not giving you the actual physical answer, but in an analogy, that's how you would think about it. That the universe was sort of bubbling along in a quantum way, and the ripples got frozen as it grew. What we are seeing is what it looked like 375,000 years after the Big Bang. What I'm describing to you happened like microseconds before, after the Big Bang. So, the physics is, we understand some of the physics, and some of the physics is still up in the air.
Thank you.
Yeah, just wait for the mic.
Is the simulation only about the visible universe or the whole universe?
So if you mean by the visible universe, things
yes, our understanding of.
So if you mean by the visible universe only things that we can see, like ordinary matter, the answer is no. Ordinary matter makes up only a small fraction of the total matter in the universe. Most of the matter in the universe doesn't glow. It has mass, it responds to gravity, but it doesn't glow. So the very first simulations I showed you where there was pink and blue forming, that's made up of all that matter that does not glow. That sort of forms the skeleton structure on which the baryons, the ordinary matter, gels and flows into. We also model that. But if you mean by the whole universe as in the size of the universe, we can't do that. We can't do the whole universe. It's too big and too expensive to do it on a supercomputer. I would burn up so much time. Nobody would give me that much time. I can't convince Hollywood to give me that time. But yeah, we don't do that. We can't do that.
The rate of expansion of universe has been in dispute for some few years. And
I'm not sure it's been in dispute. It's been more or less settled as it's been stable for the last few years. All I said was that tomorrow you might get new results from Euclid or from DESI, this dark energy survey, that'll give us a different way of thinking about where we're going. But we know what's happened in the last 4 billion years. We know that the universe is expanding at a certain rate. We can measure that.
the universe is expanding faster than light. Is it possible some sections of the universe is contracting faster than light? Is universe expanding uniformly everywhere, or is it shrinking somewhere and expanding somewhere?
Not in a global sense. On the large scale, think of a balloon. Balloon can expand, and everywhere it'll expand in the same way. Now, tiny little bits on a balloon where a black hole forms, you can have a dimple. Around that dimple, the space can collapse and contract. But the whole universe as a whole is sort of expanding uniformly and expanding very, very fast. and expanding. Yeah, it's in a way it's expanding such that things that are far away look like they're moving away from us faster than the speed of light.
Other than black holes, could there be a possibility of contracting space-time?
I can't think of anything off the top of my head. Strong gravity would contract, and the strongest gravity areas where strongest gravities that I know of are black holes. Yeah.
Can we take one more question? Yeah.
Yeah, hi. Thank you, sir. So you briefly mentioned about the black holes. So do all the galaxies that you just showed um, right from the beginning of the time, do all of them have a black hole at the center?
So that's another really interesting question that's come out of JWST. What we thought was that initially galaxies would not have big black holes in the centers. It would take some time, because what's a black hole, right? Gas has to collect. If it's a large star that blows up, turns into a black hole, then more gas has to fall in for this black hole to keep growing bigger and bigger. And we thought all that would take, hundreds of billions of years. What we're discovering from JWST that it happened very, very fast. So trying to make sense of that is an interesting puzzle. One of my colleagues, who actually is also related to Chandra, has put out this idea that what we thought about black holes forming through small clouds and then growing is not correct. The way you should think about it is that big clouds collapsed really fast. At the same time that the galaxies were forming, those galaxies I showed you, in the centers, big clouds were collapsing and forming these massive black holes.
Okay, so it's not just the death of a star that forms a black hole.
No, you could have a massive collapse that would not even form stars. It would just collapse altogether into a black hole. Yeah.
Thank you, sir.
It happens more easily in the early universe than it would today. But yeah.
So when you showed those nurseries where the stars are born, why doesn't it happen there? Why do the stars still get born?
So stars.
Why do the stars still are born? If the gas can collapse and form a black hole.
Oh no! So today, okay. So let me try and describe this pictorially. So if I have a box of gas or a sphere of gas, and I cool it, but I don't do anything else to it. I just allow it to cool more or less same everywhere. Then every part will just fall in, collapse, and then it'll form a big black hole. But the universe today is not like that, because we've had many, many generations of stars going through. And one of the things that stars make, people often say we are dust. Why? Because the stuff we are made up of, iron, carbon, nitrogen, this is stuff that's made inside the stars, and then when they blow up, they shoot it out. And eventually planets form that capture this gas. And anyways, long story short, these carbon, nitrogen, oxygen, iron, they radiate faster. So imagine I have a big sphere now, and there are patches of these iron, carbon, nitrogen. This part is going to cool faster. So now it's not going to collapse like this, it'll collapse like this. Then you will form stars. So this is why I said in the early universe, before all the stars formed and all that carbon, nitrogen got spread around, it was easier to form black holes. Today, it's easier to form stars than it is to form black holes. You have to wait till a star dies, and it has to be a big star in order to leave behind a black hole.
All right, thank you, sir.
Okay. Thank you everyone for this amazing questions. Before we end, let us thank Dr. Arif Babul for this amazing lecture and answering these questions so patiently and nicely. Thank you so much.
Thank you very much. It really had nothing to do with being patient. I enjoyed the questions. These were some of the toughest questions I've gotten in a public lecture.
Yeah. So,
you have a question?
Yes. Why
doesn't? Oh, come on, you say. You say. You say.
No, go ahead. Don't worry about it.
Why?
Just say it.
Why doesn't elliptical? Oh, come on! I hit my head.
No, it's okay.
Why doesn't elliptical galaxies? Oh God damn
Collapse.
it!
Fusion collapse. Okay.
Why don't spiral galaxies collapse?
Ah, that's a great question. Because they're spinning.
No, the elliptical.
And the elliptical galaxies stars are doing this. They're just moving around, up and down, in and out. So you know that picture I showed you? Give me a second, I will find it. There, I think that's it. Yes, that's it. Okay, so I was talking about clusters of galaxies, and these things are galaxies. So let's forget about the fact that they're galaxies. Now let's look at one of these guys. This is an elliptical galaxy. It's made up of stars. Okay, I can use the same picture. Now imagine that these are not galaxies, but stars. They're moving fast. They're moving at hundreds of kilometers per second, but they can't escape the gravity. So they are stuck together, they move, and when we look at them through a telescope, they look like an elliptical galaxy. Spiral galaxies don't do this, where all the stars in a spiral galaxy just swirl around like in a pizza. And so they look like spiral galaxies. Good enough?
Yes.
Did I answer your question?
Yes.
All right, excellent.
Okay, thank you very much. Also we'll be coming up with our next lecture very soon. Please be in touch with our social media account, and we have like very nicely updated social media. So please be connected with us for the next lectures. Thank you for coming, and have a great evening. Thank you.